Next speaker is Marc Vinyals. Marc, can you share your screen, please? Yeah, so Marc is a postdoc currently at the Simons, and before that he was working in the Technion. He's a visiting fellow at Technion with Yuval Filmus, and he did his PhD under Jakob Nordstrom at the KTH in Sweden. And without further ado, Marc, the floor is yours.
Right, thank you, Vijay. So, yeah, keeping with the topic of the workshop, I'm going to talk about how we can use proof complexity to talk about solvers. And this time, we're going to go really, really deep into the guts of the solvers and talk about the actual heuristics being used in the solvers. So let me quickly recall our beloved CDCL algorithm, which is based on DPLL from the 60s. So in DPLL, we have a formula and we branch on variables. If there's a unit variable, we propagate it. If there's a conflict, then we backtrack. So in this example, we would branch on X, branch on Y, then get a conflict with Z, backtrack, and so on. Now, the change that CDCL introduces is that we can learn clauses. So, for instance, here at the first conflict, we are able to learn that constraint Y must be true, and now that's great because when we backtrack past X, and now this time because we have already this clause, we can use it and we can avoid having to traverse part of the search tree again. Okay, so now let's get proof complexity into the picture. And this is actually a quite easy thing to do. It's enough to look at the CDCL execution trace and just reverse all the arrows. Right? So while we had arrows pointing in the direction, now we reverse them and we get a perfectly valid resolution proof. Now, because this is CDCL and we have learning, we're also going to have some arrows that come from previous parts of the search tree into further parts of the search tree, like here. So the proof is not going to look like a tree, it's going to look like a general directly specific graph instead. And in fact, this is what distinguishes CDCL and DPLL in the proof complexity world. So while DPLL only produces proofs that look like a tree, so that would be tree-like resolution, CDCL produces a more general kind of proofs. And since we know that tree-like resolution is weaker than resolution, then we can say, this is a great reason for why CDCL should work better than DPLL. And of course, the question still remains whether CDCL is as powerful as general resolution, or is it maybe just some subset of that, like DPLL is. This is a question that was investigated during the early 2000s, and it was answered in 2009 by these couple of papers, showing that, yeah, CDCL proofs are roughly equivalent to resolution proofs, at most up to some polynomial factor difference. That result, however, needs us to make a few assumptions on the model. We have to assume that we are using optimal choices of variables. We have to assume that we don't throw away clauses. We have to assume that the solver restarts frequently enough. And we also have to assume that the learning scheme is a reasonable one, such as first to IP. But let's just focus on the theorem itself. We have that CDCL can efficiently find resolution proofs. Now, like Susanna told us that that's impossible if unless P is different from. Let me rephrase that again. If there were a deterministic algorithm that could efficiently find resolution proofs, then P would be equal to NP. So what's going on here? Well, that's of course because of the assumption that the solver makes choices. This result that CDCL can efficiently find resolution proofs to work, we need to have an oracle that every time that the solver wants to branch, so fix the value of a variable, the solver would ask this oracle, okay, please tell me a variable. Now it will branch on that variable, and so on. And it has to do that every time that it wants to decide a variable. Now, this is, of course, a strong assumption. We can weaken it. For instance, if we have random decisions, then we can have a similar result saying that now CDCL can simulate not resolution, but bounded with resolution, which is a smaller class, but still quite important. But then what happens if we go and plug in here not optimum decisions, not random decisions, but the kind of heuristics that solvers would use in the real world? Well, then we no longer have a simulation. We, in fact, have that CDCL and resolution are exponentially apart. So more precisely, there are formulas that have resolution refutations that are short, just polynomial length. But if we want to find out that they are insatisfiable using CDCL, that would take exponentially long time to do. As long as we're using these common partial decision heuristics.
So Marc, this is more like a non-automatability kind of result under the assumption that the branching heuristic is VSIDS. Is that fair?
Exactly. So yeah. So while the result of Heuristics tells us that non-automatizability, if you assume P versus NP, this tells us the same, but assuming these heuristics instead. So it's the result that doesn't depend on P versus NP, but it's limited not to any algorithm, but only to the CDCL with these heuristics. Yeah, thanks, Vijay. Great. Well, let's talk about the decision heuristic with more in depth. And so we are at this part of the solver where we want to branch on a variable. And we're trying to answer this question literally now going fixed. And it's really not obvious what a good literal would be. That's why we had to assume an oracle before. What solvers try to do currently, or at least an explanation for what they are trying to do, is that it seems that a good idea is to pick a literal that will quickly lead us to a conflict. So we would like to avoid having to do many propagations, many further decisions. So if we can get to a conflict as soon as possible, then we're happy. And the way to try to achieve that is to pick a variable that has been involved in a conflict recently, with the hope that, yeah, if it was involved in a conflict, when we're probably in a part of the search space that is close to that, then chances are that we'll get another conflict soon. And this is how the VSIDS heuristic works. So we give a score that's a real number to each variable. Initially, the score is 0. And now every time that we hit a conflict, if a variable has been in a conflict, then we increase its score by 1. And if it hasn't been in a conflict, we do nothing. And now and then we multiply all the scores by some number that's less than 1 so that they decay in time. So this is just implementing an exponentially moving average function. And when we want to pick a variable, we just go and pick the variable that has the largest score. About the sign, here it's usually combined with the phase-saving heuristic, where we assign the variable to the same polarity that was last assigned, the last time that we saw this variable in the tray. Right, let me make another observation about VSIDS. Let's think what happens when we have a variable that is in a conflict. Then its score, it's always going to be positive. Right? It first gets increased by 1, and then it's stuck, but it stays positive. While a variable that has never been in a conflict always has score 0. So that means that a variable that has been in a conflict is always picked before a variable that never has. Now, this is true in theory, maybe not so true in practice. So if we assume that we have unbounded precision numbers, the scores have infinite precision and they're real numbers, then this is true. If we implement them with doubles, then it might be that a variable is in a conflict, and then a lot of time, there's a lot of time in between conflicts, and the score might decay to a number that's so small that we cannot represent it, and it then gets rounded down to 0. And then what happens depends a lot on the exact implementation of the solver. So if the solver uses a stable data structure where numbers with the same score are not rearranged, then this observation is still true. If it has another kind of data structure, then it might not be true. But again, things start to get messy, so we're going to just assume that the observation holds for now. Great. I want to give you now a bit of an idea of how we could try to build a formula that has these properties, that it's easy for resolution but hard for physics. And yeah, let's start with the first thing you could think of. Let's just have two formulas, one that's easy, one that's hard. We, of course, want to have a formula that's easy because that to be an easy short proof. And it seems that it would be a good idea to have a formula that's hard because we want to trick the solver into solving that hard formula. Yeah, just for the proof complexity experts, think of this hard formula as an exponentially formula required in exponentially long proofs such as cheating. Anyway, so let's see that the solver starts talking about some variables in the hard part, like here, and reaches a conflict. Then these variables have their score increased, and that is going to lead us to more conflicts in the hard part. So we're doing well. That's what we want to happen. But these hard formulas have a very global structure. So if you only assign a few variables, then it's always possible to find a satisfying assignment. So what's most likely going to happen is that after a couple of clicks, now the current assignment will be satisfying the hard part, and then the solver is again free to go and choose any literal that it wants, and maybe now it will start talking about the easy part, reach some conflicts over there, and very, very quickly go and solve the easy part. So that's not what we want. Okay, then let's try to make life harder for the solver. And we're going to add some more clauses. So a specifically crafted gadget, just a set of clauses with the following property, that when the solver starts assigning variables from the gadget, then suddenly it will start unit propagating and start talking about all the formulas in the hard part of the variables in the hard part of the formula. And after it's done that, and it's talked about all these variables, then it will reach a conflict. So now that's awesome because all of the variables in the hard part of the formula have now positive score. So score 1 at least. And now the next conflict will necessarily have to involve variables from the hard part because the score is positive. The next conflict also will have to do that, and so will have the next conflict. And of course, there might be some variables that are elsewhere in the formula, but since their score is still positive, the solver is now stuck here. It must always pick variables from the hard part of the formula. And because we know that, so that the solver will end by proving that the hard formula is false. And because we know that there's an exponentially long proof of that, or rather that all proofs must be exponentially long, this tells us that to find that proof, the solver must have taken exponentially long time. Now, this is almost it. There's only one small thing that we still have a small but non-zero probability of solving the easy part first, right? This was true if the solver started talking about the pitfall gadget, but maybe it starts talking about the easy part, and what do we know? So in order to fix that, we can also add a few more clauses that will make the solver, so when it starts talking about the easy part, it will automatically shift its attention to the pitfall gadget, and then we are in good shape because the pitfall gadget will propagate and all the previous reasoning will hold. Now, to talk about this, the only thing that we used about the heuristic was really this property that a variable that's been in a conflict will always be picked before a variable that has never been in a conflict. And this is a property that not only VSIDS has, but most of the heuristics currently in use have this property. So variable move to front, VSIDS, CHB, LRB, all of them has this property, and they will be tricked by this kind of formula. Also, the results hold. The result holds no matter whether you have or you don't have restarts. But interestingly, it doesn't hold if you clear the score of the variables when you restart. And Ian is going to talk more about this in a while. Now, you might be thinking, yeah, this was some theoretical work and looks very theoretical, but what can you tell me about this in practice? Well, let's see some data. So here in this table, we have 4 solvers, each with a different heuristic, so VNTF, VSIDS, CHB, LRB, plus a 5th solver that uses an oracle. So it's a finely tuned heuristic. And now in each of the rows, so I have 2 formulas, one instance of just the hard part, so the big red scary part, one of size 45, one of size 50, and they are chosen so that the first one is hard to solve but can still be done within an hour, while the second one is just a bit and cannot be solved within an hour. And that's just impossible. I mean, it can never be quick because it's just hard. There's no matter how we try, any solver using resolution will never be able to solve this. While if we look at this tricky example, so there are 2 formulas here. The first one is based on the first hard formula. The second one is based on the second hard formula. Now what happens is that it stays roughly equally hard for the normal kind of solvers. But now, of course, we know that this formula does have a short proof. So it's possible to find a great decision heuristic that's finely tuned to this formula and makes the solver run fast. And indeed, by doing that, then we can solve this formula in less than 1 second. Just it's that easy. Anyway, so let me finish by saying that, so while we think of CDCL being equivalent to resolution, that's only the non-deterministic version of CDCL, and we should keep in mind that with the actual heuristics, that's not necessarily the case. And on problems, so I mentioned that the result is dependent on whether you have arbitrary precision or fixed precision. It would be great to manage to prove this with limited precision, like solvers have in the real world. The construction is also a bit clunky. I didn't even dare to show you all the clauses. It wouldn't make sense. So it would be nice if we could simplify this construction a bit. And then it would be great to improve VSIDS. I don't think that we should throw away VSIDS or any of these other heuristics, that they really, really work great. But it's also true that there is room for improvement. So of course, we could try to learn the lesson from here and improve these heuristics. So thanks.
Thank you, Mark, for a fantastic talk. Yeah, it was wonderful. I was wondering if there are any questions before I ask mine. So Dimitri has a question. It says, is there any satisfiable formula that is provably hard for CDCL with some heuristics? Mark.
I know some early results from Alechnovich and others. Yeah, Vijay?
No, Dimitri, Ian is going to talk about it actually. But there the
great.
idea would be...
Sorry. Yeah, Lechnovich, Hirsch, and Saxon gave an example for DPLL solvers. What I'm asking, is there anything similar for CDCL?
Yeah, yeah. So there is a talk in 20 minutes. My student Ian will talk about exactly such formulas. But there, the heuristic that we switch on and off is restarts, not the... So, Mark, I think some of the work in improving VSIDS that you're referring to, one of the things that your work suggests is kind of refocusing the branching heuristic at regular intervals, not necessarily zeroing out the activity, but maybe one way to refocus. The term refocus here means, as you well know, across restart boundaries, we maintain the activity heuristics. We don't throw them away. And usually it's not a good idea to throw the activity of the variables, but perhaps it may be a good idea to change the activity of the variables through some heuristic. And I think that might be that heuristic where you refocus the activity could be tested against your class of instances to see whether it helps solve those instances more efficiently.
Yeah, exactly. And we do know that if you do this throwing away the activity, then the solver will run fast on these instances.
Right.
But of course, we don't want to do that, right? So it would be very
exactly. We want to find that balance where we do well on your instances, but also on SAT competition or verification instances. Anyway, this was a great talk. Thank you so much, Mark.